Alright folks, here we are in the second part of the review number 1 for statistics, and we're looking at a problem here. We've got the height of maize plants somewhere is normally distributed with a mean of 1.62 standard deviation. We don't know. The probability the random chosen plant is greater than 1.8 is 0.15. Find the standard deviation. Alright, so we know it's a normal distribution. And we know what the mean is. We don't know what the variance of the standard deviation is. So we know that the probability of the height being greater than 1.8 is 0.15. All right. So if we get a quick look at this, we can see on the graph that if it's greater than 1.8 and that the area is only 0.15, it's got to be on this side of the mean. Now 0.85 or 85% is on the other side. My table goes that way. So the z-score I'm going to find is going to actually be represented by 85% or 0.85. See, the whole thing here is I'm going to make a z-score equal to a z-score. I'm going to take the 1.8 and change it to a z-score. And then I'm going to take this 0.85 probability and change it to a z-score. So I think that some people got confused by this before when we were doing it in class. What we're doing is we're making these two both z-scores, then they'll be equal, and then we can figure out what the standard deviation is. So if I go 1.8 minus the mean, and then over standard deviation that I don't know, call it theta, and then it's equal to whatever the z-score matches up with 0.85, and I think it's 1.0355. You should double check that. And see, now all I got to do is get the standard deviation by itself, multiply both sides by the standard deviation, and then clean that up the one side, and then divide. And when you do, you should find out that the standard deviation is 0.174 to 3 significant figures. All right, now in this next one, it says the faces of a biased die, well, 1, 2, 3, 4, but it's biased. That means that the probability is going to be different than we would expect for a normal fair die. Now we do know this probability distribution, they all should add up to 1. So if I take the 4 p's and add it to 0.4, it should equal 1. So now I can find out what p is equal to. P is going to be equal to 0.15. And see, now I know the probabilities of these guys that we're missing, because they're all the same. All right, now what? Find the probability that the score is 4 and not more of 1 in 3 trials. 3 throws. That's a trial. 3 trials. And this is a yes or no situation. So trials and yes or no situation is a good sign that's a binomial distribution. So it's not a big enough number of trials for us to use a approximation, normal approximation. So what we're going to have to do is use the combinations. So anyway, we got this binomial distribution, and we have 3 trials, and the probability of a success, p, is 0.15. So we got 3 trials, that's 3 combinations 0, that's going to be 0 x's. And we take the probability of success to the 0 power and the probability of failure to the 3 minus 0 power, or 3. We multiply those together, and we get a nice little decimal. And then we got to go and we got to do it again, because we got to do it for 1, the probability that it's a 1, because we're talking about not more than 1 out of 3 trials. That means it could be a 0, and it also could be a 1. So the probability of it being less than or equal to 1. So we go ahead and do the same kind of thing that we just did. Oops, let's try this again. 0.15 to the first power, and then 0.85 to the second. And then we multiply these together. And again, we can get a nice decimal. And then when we add those two together, we should find out that the probability of both of those things happening, 0 and 1, is 0.939, 3 significant figures. All right, number 3, the probability that the school bus is on time on a particular day is 0.6. And if the bus is on time, the probability that Sam, the driver, gets a cup of coffee is 0.9. If it's not on time, then the probability drops. So we've got two options here. First, you'll notice that he can be on time or he can be late, and we've got a probability for each one of those. Then we've got two more options. He gets a cup of coffee or he doesn't get a cup of coffee. And once again, we're provided with probabilities. And even if they only give me one, if I know probability of the one, I can figure out the probability of the other. So this is a great situation to use a probability tree. So we start off, we got our first decision to make. The first is whether or not we're going to be on time or late. And again, it's not really a decision, but we know the probability of it being on time is 0.6, which means probability of being late is 0.4. And now the next thing that happens is, in either case, either I get coffee or I don't get coffee. And there's a probability for each one of those situations. If I'm on time, I can get coffee, and the probability is going to be 0.9. And that means that if I'm not going to get coffee, it's only 0.1. And if I'm late, well, it probability drops to 0.3 to get coffee, so that means not is going to be 0.7. Well, keep in mind when doing a probability tree, you multiply across to find the probabilities of each of these things happening. And I'm going to write all this out. You really don't have to. But the probability of being on time and getting coffee is going to be 0.6 times 0.9 or 0.54. The probability of being on time and not getting coffee, no coffee, that's going to be 0.6 times 0.1 or 0.06. The probability of being late but still getting coffee, that's going to be 0.4 times 0.3 or 0.12. And the probability of being late and not getting coffee, worst scenario, that's going to be 0.4 times 0.7 or 0.28. Now if I add all those up, they should add up to 1, and they do. And so I'm feeling good about the fact that I got the right stuff. And so now all I got to do is figure out what's the probability of getting coffee. Well, there's two chances for that to happen. Either I'm on time, I get coffee, 0.54, but I also could get coffee if I'm late, 0.12. I add those together, and then I get my probability of getting coffee, whether I'm late or not. Now the second part says that given Sam does not get a cup of coffee, find the probability that the bus is not on time. So we have the conditional probability formula. The probability that A is given B is equal to the probability of both of these things happening divided by the probability of the given thing happening. And so it's a good idea to rewrite that into what we actually are talking about. So the probability of being late given that there's no coffee. All right, so that means we got to find the probability of being late and not getting coffee and divide it by the probability of just not getting coffee. All right, so let's take a look up at our thing here. We can see pretty quickly that if I'm late and I don't get coffee, that's a probability of 0.28. And then just not getting coffee, well, that happens twice, 0.06 and 0.28. I add those together. And so now all I got to do is simplify this and then divide. And I find out that the probability of getting coffee is 0.824, 3 significant figures. Now in number 4, I've got a box that's got 2 green sweets, 5 blue sweets. 2 sweets are taken out at random without replacement. They want to find out the expected value. The random variable x is the number of green sweets taken, and they want the expected value and then the variance of x. So we need basically to know all the possibilities for x, how many different things could happen as far as getting green sweets. And I need to know the probability for each one, because remember, when we have a probability distribution, I can find the expected value if I multiply each of the x's times its probability and add them all up. So the sum of all the x's times its probability, that's going to be the expected value, or the mean. And then to find the variance, I've got to square the x's and then multiply them times their probabilities and then subtract them from the mean squared, which we just figured out. So the expected value is the same thing as the mean. So now let's go ahead and do this. All right, so let's see. It's possible that I could get 0 green sweets. I could get 1. I could get 2. That's the most I could get, and that's the least I could get. So now I've got to do is find the probability of each one of those things happening. And there's probably more than one way to do this, but I'm just going to go ahead and use multiply. We got 2 things happening, and so the probability of 2 things happening is the probability of each one multiplied times the other. So 0 green. Okay, well, the probability of not getting a green at all, there's 5 blues, and there's 7 sweets altogether. So if I'm not going to get any green, that means it's going to be 5 out of 7. And then I multiply it times 4 over 6, because now there's 1 less. And so now I can find out that that's 20 over 42. Now, if there's just 1 green, well, there I got 2, so I just can get 2 out of the 7. That'll give me my 1 green. And now I'm going to have 5, but only 6 left over. So when I multiply those together, I get 10 over 42. But here I got to be careful, because here I just did it this way. I got a green one first. Well, what if I got a non-green one first and then a green one second? Well, that's another way this could happen. And so I've got to take that into account. So if I got a non-green, that would be 5 out of 7. And then I got a green, that would be 2 out of 6. And you'll notice it's still the same thing, but I've got to add those together, and I get 20 out of 42 for 1 green. Now, for 2 greens, there's only one way that could happen, as it was with 0 green. There it's going to be 2 out of 7, and then 1 out of 6. And then multiply those together, and I get 2 over 42. Now, I got my probabilities. I know what I'm going to have to do is multiply and add them together. So I'm going to go ahead and simplify these. They don't seem like they're really that difficult to simplify. So 20 out of 42, that could be 10 21sts, and then this one's going to be the same, and then 2 out of 42, that's going to be 121s. I'm going to double check. If I add them up, I still get 21 out of 21. All right, so now I'm going to take 0 times that probability, which is 0, so I'm skipping it, and then 1 times 10 over 21, that's 10 over 21, and 2 times 1 over 21, that's 2 over 21, and I add those together, and I get 1221, and that's my expected value. And I reduce it to 4/7, and then I can change it to a decimal, 0.572. All right. So now I've got to find the variance, and I'm not going to have enough room here, so we're just going to kind of go down here. All right. So the variance is when I square the x's and then multiply and times each of the probabilities. Well, again, I'm going to write it this time. 0 times the first probability is still going to be 0. 1 squared times 10 21sts, and then 2 squared times 1 21st. Well, that's just going to be 10 21st, and that's going to be 4 21sts. And then I've got to make sure I don't forget to subtract 4/7 squared, which is 16 to 49, so you could write it like this. And then all I have to do is let the calculator do the work. You can find out it's 50 over 147, or 0.34. All right, 3 significant figures. Hope that helps. I'm going to put the rest of them on a different video. Okay, thanks for watching.